Hello and welcome back to the Fullerton College Prepress class. This is your professor, Ben Hewitt. Today we're looking at PIA's Prepress Trainee Manual, section 6.3, Advanced Output. This is going to be a bit of a technical chapter to talk about, but the technical details contained in this chapter are pretty valuable stuff, and I'm quite happy to get to talk about it. Bear with me if it gets a little bit detailed, but these are the details that do matter to creating a successful, good-looking printed piece. We're going to talk specifically about how a RIP translates computer-based pixel data into halftone screened data to be used on press. Really, this is the nuts and bolts. This is looking at, in detail, the translation process between what your computer can generate and what a printer can print. If you want to understand how to make something survive that process, you need to know the process. So we're going to talk about things such as, but not limited to, raster image processing and what it does. We're going to talk about spots, cells, and halftone dots and what they do to make the various amounts of gray levels you're capable of having. And also why gray levels are the most important thing in creating good imagery, and especially in creating good color. Lastly, we'll also talk a bit about different types of screening, because there's continuous tone, there's halftone, and there's stochastic. They all have their uses. Some of them are more feasible than others, and I'm really excited about some of them. So let's get started without any further ado. So output, we already know from previous chapters that prepress workflow used to be a bunch of individual stations that were separated by physical distance, and things were done by hand. Back in the days of film and large process cameras and exposure tables, very similar to how you make screens for screen printing, used to be how you'd make plates for plate setting and for then printing on an offset lithography. By computerizing and automating a lot of this stuff and being able to use digital files instead of knives, rulers, and glue, we're able to do things much more efficiently. And it also then integrates a bunch of steps that used to be a thing. So we have our PDF creation, our pre-flighting, our trapping, imposition, RIP, and output. So once again, we're looking at this diagram of the prepress workflow. So the workflow solution is the series of computers that does the things necessary to the file to make it ready for output. It can take either PostScript or an already made PDF, and it can take those and process them to impose them, to trap them, to rip them, and get ready to output on a marking engine. Well, this time, we're going to talk specifically about what happens between the workflow solution and the marking engine. The workflow solution sees images one way, the marking engine sees them another way, and we need to talk about how do these two languages translate? Where do they meet? How does one affect the other? How are they similar? How are they different? This is an important concept because you might just talk about resolution and dots per inch. But the resolution and dots per inch for a computer image is vastly different than what it means when you're talking about the resolution of a marking engine, which is then still different than talking about the resolution of a halftone screen. There aren't quite enough words in our language to describe the specifics. They all just fall under the phrase resolution. But resolution on a computer screen is not the same thing as what actually ends up on the paper. There's a translation process, and we'll go into the whys and the hows shortly. So the raster image processor, the RIP. The RIP takes PostScript or PDF and turns it into a pixel-based raster image. Raster is another word for a pixel image. The number of pixels the machine can do, the number of machine pixels per linear inch is called the output resolution. Now, a machine pixel is different than an image pixel you have in Photoshop. We'll get to that in a minute, but just know that it's not the same thing. When you hear pixel, yes, it's the same idea, but machine pixels are a little bit different than the ones you'd normally be used to using in other pixel-based image editing software. So high and low resolution devices. I know you guys have heard enough of me already to know that if you're talking about resolution on a computer screen of a Photoshop image, what do you need to print cleanly? Gosh, that's why I like you guys. You all got it right. It was 300 dots per inch. You're right, at the size you're going to output. 300 dots per inch is great for a computer raster image. However, 300 dots per inch is insufficient for an output device. Output devices have many more dots. A typical, not a very good, a typical, normal, average, run-of-the-mill, mundane plate setter is looking at around 2,540 dots per inch linear. That's a bit more than 300 or maybe even 600. Now, one of the disparities here is a lot of proofing systems and digital presses are limited to 300 or 600 dots per inch of actual output resolution. The best digital printers, not counting the HP Indigo, which is a totally different ball game, and we're not going to talk about that today, but that uses a very different system, so it's able to do things other things can't. But all toner-based systems are going to be limited to about 1,200 dots per inch, never more. Why not? Isn't the technology there? Can't we make finer toner particles? Can't we get it to make them to print smaller? Well, yeah, we can, but it's not a good idea. Digital printing, especially the toner-based stuff, is at its limits of what is safe to use. If you make those toner particles smaller to be able to get more resolution out of them, you could do that, but then the person operating the press has to wear some extremely good PPE to protect their lungs from the toner. Once the toner becomes a particle of smaller than 1/1200th of an inch, well then, you're running into asbestos type problems when you're going to be able to give people lung cancer by working with a printing press. And really nobody wants that. That's not good for business. That's not good for anybody. Nobody wants that. So digital printers are capping out at 1,200 dots per inch. They will not ever, I mean, maybe some really, really good inkjets might manage it. And I know the HP Indigo does, using a more liquid solution to float their toner particles inside of. They do it a little bit different as a digital press. But if we're talking electrostatics, the best you're going to do is 1,200 dots per inch. It's not going to increase from that unless they find some way of safely using the toner in a way that can, not kill the user in one of the most horrible ways to die. Anyways, so high and low resolution. Now, another resolution is called lines per inch. Lines per inch is talking about the number of halftone dots you can have in an inch. They also call it the frequency or the screen ruling of the print. And that's counting the number of actual printed spots on the paper you can get in 1 inch. So, making halftone dots. This is the exciting stuff. This is the part where we start to talk about the translation of computer pixel to machine pixel, and from machine pixel to halftone dot. Excuse me. So halftone dots are created on a microscopic grid that looks a lot like this one. Yeah, it looks like you bubbled in graphing paper. That's kind of how it thinks about it. It's like a graph, and then it makes the spot larger or smaller by taking up more or less squares, because again, all printing, even the most advanced printing in the world, in the end only answers a yes or no question. All marking engines are only able to answer, is there ink here? The better marking engines answer that question in a much more detail over a much smaller area. The cheaper or less fine precision machines, they still answer the question of yes ink or no ink, but in a much more blunt, wide, fat marker tip kind of thing. So the number of cells per inch can be changed independent of the output resolution. You can change how many cells you have per inch. That changes the number of halftone dots per inch and the number of machine pixels in each halftone dot. So there's a couple different things at play here in tension with each other that are going to create your ability to show small differences. Because the number of machine pixels that you give, you know what, I'm going ahead of myself, but I'll say it anyways. The number of machine pixels you give to any particular halftone dot is the amount of variation you're able to have within that halftone dot. That's vital. We'll get back to that. So the marking engine sends the machine pixels to the marking engine. So the RIP sends the machine pixels to the marking engine, and it's made up entirely of on and off commands. On, where it wants to, well, actually I have to I can't say that. Depending on if you have a positive or negative acting plate, this will be different depending if the laser activates the print area or if the laser activates the non-image area of the plate. That can change. So I'm not going to nail this one down by saying definitively, but the whole image is based off of whether or not it's going to shoot a laser at a part of the plate. And depending on the plate, the laser will either make it accept ink or make it accept water. Depends on the plate. So this information then becomes a series of motions for the small servo motors inside the plate maker that move a tiny laser or a little lens that focuses the laser around back and forth over the plate to spot each little tiny pixel. And it has such fine motor control. Remember that number, the 2,540 dots per inch? Those are all individual laser zaps. Each one of those is one little tiny beep of a laser. And that one little tiny beep of the laser is going to make that spot do what you want it to do to the size that it's able to do it. Spots on the marking engine. So the marking engine takes these instructions to the bilevel bitmap, and for every on machine pixel, the marking engine creates a mark on the output media. We'll do on assuming that the lasers are going to make print area in this one. So each spot, as you can see on here, covers a machine pixel. And these spots are still about 1/2400th of an inch. I would say it's pinpoint accuracy, but I looked that up because I was curious. And it turns out the tip of an average sewing pin is 5/1000ths of an inch. The laser spot, in fact, is 1/2540th of an inch. It ends up mathing out into the decimal to be about 10 times smaller than a pinhead. That's right. You could print 10 machine pixels on the pointiest tip of a pin. That's the size we're talking about here. It's very, very, very focused. Anyways, so these spots shoot each one of the machine pixels that would have been an on spot. So the 2400 dots per inch means each side of the machine pixel is 10 microns long. At 150 lines per inch, which is kind of what you think of as 300 dots per inch, if you remember your Nyquist theorem, we're looking at 16 pixels by 16 pixels. Now 16 and 16, those are already pretty computer happy numbers, but when you multiply them together, there's our old friend, 256, coming back to say hello. 256 pixels. Each laser spot covers one square of one machine pixel. So spots and gray levels. Halftone dots need to show hundreds of different shades, not just whole percentages between 0 and 100%. It's not just like you need the ability to have between 0 and 100 sizes in there. The number of spots used to make a halftone dot controls the number of shades you can do. The more machine pixels per halftone dot means more gray levels. The number of gray levels is how fine a control you have over the lightness and darkness of any given image. That also therefore means that that's how much you can control the color mix, because a color mixed on a 4-color press is the result of various levels of the primary colors printed on or near each other. The more you're able to control the specific gray levels or the tonal ranges of the 3 primaries and black, the more colors you're going to be able to print. So in fact, image resolution directly, when I say image, I mean plate resolution, directly affects the amount of colors you can produce using CMYK. Lower resolution doesn't just mean jaggy images. Lower resolution means fewer choices for color. How many grays? Maybe we'll come back to this one next time a little bit more, because I'm running short on time here for this video and I don't want to make you sit too long. So we'll just stop with that the gray levels controls your dynamic tonal range of your images you're reproducing. More gray levels is good, less gray levels is meh. All right, that's it for this time. Stay tuned as we talk about exactly the numbers behind this and where they all go. Thanks for watching.